Okay, the key problem to doing the modelling is to do essentially computational light scattering. And there's actually a number of methods that have been used for optical tweezers. And probably the most common and best known of these, especially in the early days, were approximate methods, specifically Rayleigh scattering and geometric optics. Now, in an overall sense, neither of these is good enough to model optical tweezers in general. They both give us some really, really useful results. So I'm going to spend a little bit of time on these. Now I'll briefly talk about some exact methods and what influences our choice of what we want. And our particular choice of method, it's not really a method of doing the calculation, it's more a mathematical formulation for expressing the problem. It leaves open a few ways to do the actual core of the calculation. It's the T-matrix method, the T-matrix formulation of scattering. And I mean, this is the problem, this is the entity that we want to computationally model. It's an optical tweezers trap. Is this complicated? There's a lot of stuff there. This is a simplified diagram anyway. The real system's quite a lot more complicated. We want to take this complicated object, calculate the transfer of momentum and angular momentum through scattering. This will tell us the force and the torque. It's not that bad. It's not as bad as this looks because this is really the only part that's interesting. We can get reasonably good results by essentially pretending we have a particle in free space with some kind of beam incident on there. This isn't strictly correct, but it's close. And all of the optical system, bringing the beam in, the microscope objective, this is essentially part of the boundary condition telling us what our incident beam is. So as far as electromagnetic scattering problems go, it's not too hard. It's one particle that's usually of some reasonable size. It's not excessively large. It's certainly not infinite. It's not thousands and thousands of wavelengths in size usually. So it's typically on the order of a wavelength or a few wavelengths. In some ways it's a nice electromagnetic scattering problem. One complication is that we have this tightly focused beam. This turns out to be one of the hardest things to deal with. And I mean, there are many, many different computational light scattering methods. Probably the fields of most interest for doing the actual electromagnetic calculations have been meteorology, where we're interested in scattering by dust particles, ice crystals in clouds. It's very important for climate modelling. About 20 to 30% of the Earth is covered by ice crystal clouds at any time. Can look at basically radar reflection of raindrops. You want to just basically see how much rain there is remotely. A lot of interest in it for astronomy because we don't tend to have much direct access. So it's much easier to look at the light scattered by astronomical dust, say in interplanetary space, cometary dust on planetary surfaces, and if we're looking at dust outside the solar system, we really have very little chance in our lifetimes of getting actual physical samples. We have gotten samples of cometary dust. This is quite useful. And a lot of radar-based applications, a lot of interest in looking at scattering from man-made objects, recognising aircraft, but this also extends to doing things like calculating or measuring the scattering, say, of flying birds. If you do well, you can try and identify the species of birds by the radar scattering. Birds are complicated, they change their shape. Most of the particles we deal with in optical tweezers don't. But here's one big problem. Most of the work, the early work, was done looking at essentially Rayleigh scattering or geometric optics. And these are approximate methods. Rayleigh scattering is valid for small particles, up to about maybe a tenth of a wavelength. If the particle's smaller than a tenth of a wavelength, Rayleigh scattering should be a very good approximation, even a little bit larger than that. If the particle's larger than about 10 wavelengths, then people will usually say that geometric optics is a good approximation. Well, unfortunately, most of the particles we track in optical tweezers lie in this gap in between. So we will need to resort to some exact method. So keeping in mind we have this gap, we're not going to get a complete story. Let's just see what we can get out of the approximate theories. Okay, Rayleigh scattering. We take essentially a small particle, it sees an almost uniform field. And okay, we've got a classic electromagnetic problem. Calculate the dipole moment produced in a spherical particle due to an applied field. So this is the kind of problem. You can find this one in Jackson, in Griffiths, in most of the major textbooks. It's an age-old favourite exam question, and a good way to introduce students to maybe some spherical harmonics and the like. And essentially, we can calculate the induced dipole moment. We can write this as a polarizability times the field. If we have a dipole moment in a field that's not uniform, then there's some force acting on it. So this would be the force on a small particle in a non-uniform electrostatic field. The magnetic version of this is what will just cause particles to be attracted to a magnet. This is just the electric version. I can say that this is also what you can use to attract small light particles, little styrofoam balls, via Van de Graaff generator. Now, if the particle is much smaller than the wavelength, this will still be correct, or close to correct, for a particle in a time harmonic field. Then we can replace this E squared with the intensity, because in our field, the intensity will be proportional to E squared. So this is our gradient force, and essentially we have a force that's proportional to the intensity gradient. It's what's responsible for our trapping in optical tweezers. So this is one thing that our Rayleigh approximation results are really good for. They tell us a lot of detail about the physics of what's going on. We just need to be a little bit careful, can we extend this to large particles, but it gives us enlightenment. If I have some black box computational model, I take some supercomputer, do some generic finite element calculation, put in my parameters, out comes a number for the force. What do I learn from that? I learn the force that will be exerted on that particle in that case. I don't learn why. Very hard to get that kind of thing out of a black box computer model. This type of theory, the numbers might not be good, but that I can get some insight into what's happening. This is really good. I can go a little bit further. My little particle with a dipole moment in this time harmonic field will have a time harmonic dipole moment. An oscillating dipole moment, it's a small dipole antenna. And this will radiate. There'll be some energy lost from it. So I can include that energy lost due to the radiation by including its radiation resistance. It's an antenna. I can characterise it by some reactance and some radiation resistance. So it's really like essentially an RC circuit. This gives it a phase shift as compared to a pure capacitor. This means that my polarizability must be complex. I must make some correction to it due to this radiation resistance, this radiation of power. And I can replace my tiniest particle polarizability with an effective polarizability with this basically K cubed term due to the radiation. And this gives me an extra term in the force due to the loss of energy. This is essentially my scattering force. I have some incident field. This thing's extracting energy from it and re-radiating. It's a dipole antenna. It radiates equally in opposite directions. This radiation doesn't contribute any reaction force, whereas extracting the energy from this incident beam does. So the force due to this, it's in the direction of the incident field. This is essentially the classical picture of this quantum picture of photons coming in and being spontaneously emitted. So if we took the average of that over many, many photons, this would describe it really well. And again, we get some insight. We can put this together. The gradient force was proportional to the volume of the particle. Now, I didn't show it explicitly, but if we had a complex refractive index for the particle, that is, if the particle is absorbing, we'd also have an absorption force proportional to the volume of the particle. So this is for small particles. This tells me if the particle is too absorbing to trap, I don't win by going to a smaller particle. I don't win by going to a larger particle. If it's too absorbing to be trapped, if the absorption force is bigger than the gradient force, I just won't trap it. The particle will be pushed out of the trap. The scattering force, on the other hand, well, we call it the scattering force. All of these forces are due to scattering. My gradient force is due to scattering. The absorption force is due to scattering. And the scattering force is due to scattering. So we should keep in mind it's just a convention to call it the scattering force. Scattering force is proportional to the volume squared. So if the particle becomes small, the scattering force will always become small, and it'll become small faster than the gradient force. So if my particle is small enough, I should be able to trap almost anything. So even something that's very strongly scattering, say gold nanospheres, that's the classic case, basically metal nanoparticles, all sorts of nanoparticles. The electromagnetic forces will act the trap there. The only problem is the forces do become small. If you don't overcome Brownian motion, then, well, you won't trap it. This doesn't take into account the Brownian motion. That's the real limit for trapping nanoparticles. That's why they have to cool the atoms down. If you want to trap atoms in something like optical tweezers in the dipole trap, they need to be cold atoms, basically. Reduce that Brownian motion. How good is Rayleigh scattering if I want numbers from it? Okay, this isn't an actual Rayleigh scattering calculation. The real Rayleigh scattering calculation will just rise up as radius cubed. This is a slight correction to the Rayleigh scattering. This is looking at the dipole moment and taking into account that the field is not uniform and the size of the particle. So the red line is essentially the dipole force, and the black line is the exact calculation. This is the spring constant in the trap. So if we have the particle at the centre of the trap and we move it to the side, this tells us the strength of the restoring force. And this is a useful calculation because it tells us roughly how large a particle we can deal with using Rayleigh scattering. And if I zoom in on the left-hand side, anything up to about 1/5 of a wavelength in radius. So this is basically 0.4 wavelengths across, almost half a wavelength across. And I'm still getting reasonably good numbers out of Rayleigh scattering. We have a nice simple analytical formula, provided you can calculate the intensity gradients, then we get some nice simple numbers, and up to fairly large sub-wavelength particles, the numbers are still reasonably good. Would you call that good? It really depends on what kind of experimental results we're going to compare them with. Is it easy to get better than 10% for experimental forces? So yeah, if this is better than 10%, it's useful, often. Okay, that's the gradient force. If I move the particle off to the side, it's only the gradient force bringing it back to the focus. If I keep the particle at the centre, right at the focus of the beam, there's no intensity gradient. That's where the maximum is. The force there is entirely scattering force. If I calculate that force, I can see how accurate my scattering force is. This is my scattering force calculation. That looks maybe a little bit worse, but on the left-hand side, it's still quite good. And up to about the same size. Maybe I'd want to stop a little bit smaller. But up to about that 0.2 of a wavelength in radius, the results are fairly good. Okay, so out of Rayleigh scattering, I get a nice insight into the physics. I get some respectable numbers for small particles. So if I have nanoparticles, little nanospheres, single molecules, single atoms, then I get some good numbers. Larger particles, I can't trust the numbers at all. So the classic method for attacking large particles was geometric optics, ray optics. I just treat the field as rays. I don't get simple analytic formulas as easily out of this, but I still get some insight. It's traditional to associate the forces due to reflections with the scattering force, because this will act to repel the particle, and to call the forces due to refraction, gradient forces. It's not quite a sort of one-to-one mapping, and what do I call a ray that gets reflected 3 times and refracted twice? Well, it's a little bit harder, but I can still make some sort of division, still see a little bit about what's happening. And we can see some very interesting physics with the ray optics picture. Here's a very simple ray optics approximation of a focused beam. This tells us something very useful. For each single ray, the momentum is proportional to the energy flux in the direction of the ray. So a converging beam like this, or a diverging beam, has less momentum than this. Here, I have my 2 rays, they're almost parallel. Their momenta are almost parallel. Their vector sum will be about equal to double the individual momenta. Whereas for my converging beam, it's only the downward components that will add. And the sharper the angle, the more convergent this is, the less and less momentum this will have. So this tells me how I can actually get a gradient force and pull a particle against the beam. If I have a particle, let's just ignore reflection for the moment. Scattering force due to reflection will just act to push the particle downwards. So let's just ignore that for the moment. If I have some particle at the focus of the trap, okay, let's approximate the particle as essentially some kind of lens. Most particles will be thicker in the middle than at the sides, because at the sides they have 0 thickness. Maybe we'll get some funny results if we have a donut, but we can treat the particle as a lens. If it's right at the focus, rays will just go through with no deviation. There will be no gradient force. When the particle's at the centre, at the strongest field, no gradient force. Well, there's no gradient there. This is what we'd expect. If we move the particle up, it makes the beam converge more. So basically, it's the converging lens in converging light makes the convergence even stronger. Then goes through the focus, diverges. This has reduced the momentum of that light, which means there must be a downward force on the particle to conserve momentum. This gets pushed back down to the focus. If we go the other way, it makes the rays less convergent, less divergent. So this actually gives the forward transmitted light more momentum. There must be an upward force acting as a result of this. This actually also shows us one case where ray optics will fail. If I do this kind of calculation and the particle is right near the focus, I can arrange a case where these two rays come out almost parallel. This will be, I'd expect, the strongest, the largest reverse restoring force. This is a really important parameter. This tells me how strong the trap is. That's the weakest direction of the trap, the weakest restoring force. So this is what tells me whether a particle will be able to escape. And this will happen when these two rays come out as parallel as possible. It's very common when I do this to predict that these two rays will be very close together. Depending on my size scales, that might be telling me I have a parallel beam one wavelength wide. Can I have a parallel beam one wavelength wide? It will just spread by diffraction. So even if you plug this number into the paraxial beam formula, it's not very good for something that tight. That'll tell you the beam's divergent. Do a Fraunhofer diffraction calculation. It'll tell you this beam will diverge. So this will predict too much momentum. It will say the beam is much more parallel than it could be. This will give me too much reverse restoring force. So I need to have basically the interesting parts of the particle not being near the focus for ray optics to be reliable. It's not enough for the particle to be big. The surfaces of the particle must be away from the focus as well. So even if I have a giant particle, I can't always trust ray optics results, especially for this, and this is an important parameter. Typically, I find ray optics predicts this to be about twice as much as it really is. Okay, if I can live with a factor of 2 in a prediction for the strongest, for one of the most important parameters, well, then I can live with ray optics. It's not always that bad. And of course I can use the same picture for a deflection to the side. It's essentially, if I move a lens off to the side, it's illuminated off axis, it'll deviate the light. This is easy. My momentum is originally straight down, ends up directed to the right, so the particles move to the left. So I get some nice pictures, I can see what's happening, but it's not necessarily so good for numbers. How good are the numbers? This is my gradient force. I said before, we often consider ray optics to be only really good once the particles are about 10 wavelengths in size. And even on the left-hand side of this, it's only about 1 wavelength in size. This is not too bad. So for our gradient force, this seems to work fairly well. Okay, this is a promising sign. Or maybe it's not a promising sign. Sometimes ray optics will give us really good numbers. Sometimes it will give us numbers that are out by a factor of 2, and we don't necessarily know which. One thing we don't get with ray optics are these wiggles. That's due to interference. If I have a particle, as it changes size, we change the optical path length through it. We get like thin film interference. The reflectivity changes periodically with the change in size. We don't get that out of ray optics. We're ignoring all of these interference effects. But they don't affect the gradient force that much. So maybe we can live with them. Well, okay, they affect the reflectivity. This is maybe a bad sign. Maybe they'll affect the scattering force a lot. So let's look at the scattering force. Oops, they do affect the scattering force a lot. So one problem with this, it'll affect exactly where it's trapped in the trap. This is something where ray optics will do quite badly. So we need to be a bit careful. It doesn't matter how big the particle goes, even for the very large particles, this is still bad, because we still have these interference effects. It's one case where ray optics is good. when our particles are not quite spherical, when deviation from being spherical gives us physically this kind of averaging. This is like an average over some range in sizes for a particle that's not quite spherical. This might be more accurate than pretending it's a perfect sphere. If the particle's a perfect sphere, ray optics is bad for the scattering force. So this means we can get some interesting results, some interesting views of the physics by looking at these approximate methods. The numbers may be a little bit better than we hoped, especially for Rayleigh scattering. And the gradient force, sideways gradient force for the ray optics, that was good. But we need to be really careful with especially the ray optics to make sure that interference effects aren't important, that we don't have surfaces near the focus. So we want to think about exact methods. And really, we can talk about two generally different classes. It comes down to, we can either solve Maxwell's equations. There's many numerical methods to do this. They're mostly slow. They're mostly painful. For a big problem, we'll need supercomputers. And if we're solving Maxwell's equations directly, typically it's a four-dimensional problem. We have to solve a problem in three-dimensional space as a function of time. This is not fun. I can also, because I'm dealing with monochromatic light, single frequency, I can maybe solve the Helmholtz equation instead. 3 dimensions of space, constant in time. That can be a lot easier. Okay, probably one of our most famous methods, our most general methods to solving electromagnetic problems is finite difference time domain. Who has used finite difference time domain? Who has not heard of it before? Okay, finite difference time domain. We have spatial derivatives in the Maxwell equations. We have some derivative of, say, electric field with respect to x. We replace that derivative with the value at this point minus the value at this point divided by the distance. So we just replace the derivatives in the equations with finite differences. Same thing for the time derivative. And we can just start with an initial condition, step forward in time from what we have at one time. We know the time derivatives, we can step forward to the next one. One big problem with it is we need to divide it up into this grid on a scale small compared to the wavelength. The standard rule of thumb is 20 points per wavelength. So if we had, say, something 10 wavelengths by 10 wavelengths by 10 wavelengths, well, that's immediately 200 by 200 by 200. We need to have 6 field quantities at each point. This is many data points. We will need a lot of memory, we will need a lot of time. 3-dimensional finite difference time domain problems really quickly grow to the point where you're talking supercomputers. Other problem is, because we use so much space to store this grid, we have to have the sides of it still in quite close. We need to be very careful with the boundary conditions to make sure that we don't have artificial reflections. If we had everything in a perfect conducting box, it would be easier, but we don't. Still, you can use finite difference time domain to calculate optical forces and torques. I've seen it done. Saw one fellow doing this and I asked him, how slow is it? And he said, it's very slow. He was dealing with particles where he had really no other choice. It's a very general method. Maybe it's overused, it's a very wonderful tool. But when you have a very wonderful tool, if it happens to be a hammer, every single problem looks like a nail. You apply it everywhere, even when it's not the best tool. The variation of this, the same kind of finite difference approximation for the Helmholtz equation, it's the finite difference frequency domain. We're discretizing the Helmholtz equation. And we've got essentially the same problems. And that's not as well known as a method. It's not as general. It's the monochromatic problems. And we can also use finite element methods, depending on what other fields you've had experience in. You might be used to using a lot of finite element methods. They'll give similar performance. Time domain finite elements methods will perform about the same as finite difference time domain. Frequency domain ones will perform about as well as finite difference frequency domain. Again, general methods. It's been used for optical tweezers, and it's probably too slow to be really useful. It's a method of last resort, again, when other methods fail. And this is why they're too slow. We need to make many calculations. It's not enough to calculate optical force on a thing at one point. We need to calculate the forces over and over again to find the equilibrium point along the beam axis. To find this accurately, we usually need something like 20 or a few more points. If you're being really fussy, you might put in 40 or 50. So just to find where the particle is, we can be up for 20 to 50 calculations. If we're needing an hour on a supercomputer each time for each point, this is not fun. We want a very fast method. And if we want to calculate then the force and torque at all sorts of positions within the track, this can easily reach thousands of calculations we want to do. So these very general methods, they're a little slow for the repeated calculations. So I'm going to talk about a method that's really it's the foundation for what we do. Next lecture, I'll talk a little bit more about how this turns into computer code. So we can represent fields by saying at this point in space we have a particular value of Ex, Ey, Ez. It's what we do in our finite difference methods. An alternative to this is to represent these fields in terms of basis functions. So I can say my electric field is equal to some mode amplitude An times some basis function. So the most famous example of this is the Fourier transform. This type of representation is called a generalized Fourier transform. And if I choose basis functions that are solutions of the Helmholtz equation, then this guarantees that my E here will be a solution of the Helmholtz equation. So I'm halfway there. Spherical coordinates are the natural choice because my particle's nice and compact. I can choose a coordinate system centered on that, and the spherical coordinate basis set for the Helmholtz equation is known. This is the vector spherical wave functions. They'll come in a variety of names. Some people will call them vector spherical harmonics, spherical harmonics. It's already been mentioned that no one uses the same normalizations and sign conventions and parity conventions. There's at least 18 different variants, so you need to be a little bit careful. But they're very nice for doing this kind of calculation. The angular momentum eigenfunctions, it turns out to be really, really simple to calculate the torque. And they give us very good convergence. The more tightly focused the beam is, the better the convergence. Most other methods, like using plane wave spectra, the more tightly convergent the beam, the worse they get. This, the more tightly focused, the better it gets. And this is essentially our T-matrix description of scattering. My incident fields, my basis sets, comes in basically two different classes. There's my TE modes, transverse electric modes, and TM, transverse magnetic modes. So I can have some A and B incident field amplitudes. As long as my scatterer has a linear response, and that's usually a fairly good thing, there'll be a linear relationship between the scattered field and the incident field. I represent the incident scattered field the same way in terms of sums over these vector spherical wave functions. And I can write down essentially a matrix vector product. I have some matrix, multiply that by the incident field, I get my scattered field. This matrix, it's often called just a T matrix, other people call it a transition matrix. It describes all of the scattering properties of the particle at the wavelength of interest. So it's a monochromatic field, only need one wavelength. It says nothing else about the illumination other than the wavelength. So I can have any incident field. Most of the work for some arbitrary particle will go into calculating this T matrix. Once I have it, I can do repeated calculations, do my 1,000 points, find the force and torque at all of them, in a nice case at less than a second at per point. So this is really very, very fast. It's efficient for repeated calculation. Just the regular light scattering people, the meteorologists and astronomers like it too, because they're interested in plane wave illumination from different directions. And to be able to do the repeated calculations with this means that it's one of the fastest ways to do looking at it in different orientations. Can I calculate this T matrix? Yes. It's not always easy. The case of most interest probably for optical tweezers is the spherical particle. Very often the particles we trap are actually spheres. They're made, little microspheres made to be as spherical as possible. Surface tension helps us. And we have an analytical solution for the T matrix. This is me theory. If we consider this for arbitrary illumination, we usually call this generalized Lorentz-Mean theory. So it's essentially one of our very few analytical solutions we get in electromagnetic theory. So we can basically find the T matrix for a sphere almost instantly. We don't need to restrict ourselves to only considering a sphere, but this means spheres are relatively easy. Compare this with, say, a finite difference time domain calculation for a sphere. That will be much, much, much harder. There are some standard methods for calculating the T matrix for other particles. Most common method, something called extended boundary condition or null field method. T matrix method was introduced by Waterman back in about 1970. And essentially, there are computer codes available. This is restricted for particles that are not too non-spherical. They need to be not too elongated, not too spiky, not too bumpy. But really, we can use any method. I'll elaborate on this next time, but a simple way to do it, if I come back to here, if my right-hand vector, my A vector, if that is basically all zeros except for one value, my left-hand side, my scattered field, that's the same as one column of my T matrix. So if I can do this calculation, calculate my scattered field, for a single incident mode, I can calculate one column of the T matrix. I can cycle through all the possible incident modes and calculate a T matrix column by column. How do I do that calculation? Any way that I want to, really. We usually, for simple particles, use a generalised point matching method. We have used finite difference frequency domain. We have used other general methods that I'll talk about next time. But really, it does work for an arbitrary particle. The hard thing is the incident field. If I can calculate the T matrix, I need to find the incident field as well. This is often the hardest thing. There are actually many, many different methods we can use. There are methods based on trying to take some extension of a coaxial beam to an exact non-coaxial beam. We have the localized approximation, which you've got rather some detail on. Localized approximation is the fastest method. We've got other basically integral transform methods we can use. The important thing is it's possible to do. You can choose which is the best method. And there's some unfortunately complicated mathematical machinery. But once you have found these amplitudes for the incident field, that's for a particular coordinate system, a particular choice of origin and orientation of the coordinate axes. You need to be able to find this at other points. You need to know this at every point where you want to calculate the force and torque. And there are essentially some analytic formulas to do this. We have a translation theorem and a rotation theorem. And that's actually where, for spheres, our computer code spends most of its time. And, okay, I said that we have some computer code for this. Next time I'm going to talk a little bit more as to what Scenic and what it does and how you might want to use it. If you're interested in looking at it, say tonight, it's available for you to download. It's a MATLAB package, so it runs under MATLAB. If you don't have MATLAB at the moment, if you don't have MATLAB available, you won't get that much joy out of looking at it tonight. But when you're back home, you're still welcome to try it again. And tomorrow I'll be talking as to exactly what goes into that and what we can do with it. Are there any questions?
Can I use this T-matrix method for multiple particles inside a trap as well, or is that only limited to a single particle?
Mostly yes, you can do multiple particles. There are three main approaches. You can just take a T-matrix of each particle, relating the fields incident on each particle and scattered by each particle, and look at all of the different particles. Now the incident field on each particle will depend on the field scattered from the other particles. So you have to solve these together. And this gives us two of the ways of doing this kind of problem. We either just do an iterative thing, start with the incident field, then add on the scattered field from each of the other particles, and then find the new scattered field, add that on, and keep cycling through. If they're not too strong scatterers, this will converge. The other thing you can do is just write that down as a giant set of equations and solve it in one hit. That needs a lot more computer memory, but you can do that. And that will tell you the force and torque on each individual object in there. So that's often useful. There are other ways to combine these T matrices into one for the whole object. And if they're all joined together, physically joined, so that one force or torque will move them all, then that can be useful. We haven't done any of that, but other people who just do multiple scattering by particles, scattering by clusters of particles, they've done a lot of work on multiple particle T-matrix methods. So yeah, it works fine for that. Except with a couple of exceptions. There's still some mysteries in the mathematics, because exactly where the sums of the basis functions will converge is not entirely known. So there are a few little difficulties. Rayleigh hypothesis is the magic word. Rayleigh did this kind of problem. He did acoustic scattering by a grating, essentially with the T-matrix method. And he just said, oh, let's just assume it converges everywhere. Some people have proved it does, other people have proved that it doesn't. So it's another one of those fun things.
Which method do you use for time varying fields?
As in not monochromatic fields?
Right.
Probably the best way, if they vary quickly over a fairly large frequency range, finite difference time domain will probably be the best. I mean, that's the really general problem. Completely arbitrary field on a potentially arbitrary particle. There's some special cases if it's a sphere. Homogeneous isotropic sphere, then you want to take the Fourier transform of the incident line and that's probably faster, but for a more general particle, just finite difference time domain. Sometimes you do have to resort to the general methods, even if they are really slow.
But for a sphere, you use the same method for that.
For each frequency component, I think that should be fastest. That's what's been done before. The French group have looked at scattering of like very short pulses by spheres, and they've gotten some nice results essentially using that kind of Fourier transform method.
Question. Let me ask you one question.
Yes.
When I did that calculation using for the Rayleigh region, discovered that the real part of the first B coefficient was provided with the gradient force, and the imaginary part with the scattering force. And then I started to think about, can I generalize that for any particle size? Or it even does not make sense?
I think that comes about simply because for a small dielectric particle, it's only the electric dipole moment that's large for the smallest part, but the force due to radiation then depends on the interference between the dipole, either the electric dipole and magnetic dipole, or electric dipole and electric quadrupole terms. So it just turns out that the magnetic dipole terms, they're the next that matter. But I think for arbitrary particles, you can't say anything that specific. They all matter.
Okay, so if there is no other questions, let's thank the speaker again.